Good morning, ladies and gentlemen. How are we all? It's good to have you here. So it's Easter holidays, and what are we doing? Well, we're doing some chem today. So this is a bit different. Normally in TT, we do a live class for a couple of hours every week, biology, chemistry, and maths. But of course, obviously, times are different, aren't they? You know, the whole kind of exam season has been brought forward by COVID, essentially. Okay, so I know that year 12s, but especially year 13s, there's going to be loads of assessments coming your way, if not already. Okay, so I am streaming live in two places right now. I'm streaming live within the TT course to all our TT members. So welcome to you guys. Who have we got in here? We got I'm going to say a few names if you don't mind. First names only: Alex, Emily, Charlotte, David, Kaya, Megan, to name but a few. And we got some people in the YouTube live as well, which is absolutely awesome. So you guys in the YouTube live, I'm going to be chatting to you just a little bit, obviously, before we start. Hussein, love you, TT. Appreciate everything you do. Thank you so much. 26-year-old never be forgotten. Oh, Hussein, thank you very much. You know, you are so welcome, mate. I'm glad that, you know, you come back and say hi, and obviously, you know, wishing you all the best in everything that you're doing at the moment. So what is the dealio? So we're going to be doing a few live sessions. We're doing Tuesday, Wednesday, and Thursday this week, and next week as well. And we've picked some of the most difficult topics, some of the most important things that are going to help you with these assessments coming up. Okay, so we're focusing on exam technique. We're focusing on some major topics. Today, I'm focusing on atomic structure. Now, that might be like, no, we did that like in September, year 12. Like, atomic structure is really easy. But the importance of that cannot be understated. Okay, now chemistry isn't like, oh, you learn this block over here, which is completely separate to this thing over here, which is completely separate to this thing over here. It doesn't necessarily work like that. Chemistry is a spider's web. Everything is linked to something else somehow, some way. And what I want to do today is look at atomic structure and talk to you about some of the major concepts and principles in chemistry where atomic structure has an influence. Now, this isn't kind of like just a flight of fancy. This is really important because if you can make those links, if you can work things out from first principles, if you don't know the answer off the top of your head, you can use what I'm about to teach you today to work things out, because there's links with atomic structure with really obvious stuff like how the periodic table works to the less so obvious stuff like covalent bonding and ionic bonding and what the difference is between them and stuff like that. So I'm going to be using atomic structure and working my way through all of the different aspects of chemistry where it has an influence. So if you understand how atoms are built and the forces that are acting within atoms and between atoms, it opens up, it just sheds a light on so much other stuff. And I hope that's what it's going to do for you guys today. Okay, so any questions in the YouTube before we start? Now, like I said, during the live, I'm not going to be looking at the YouTube chat at all. Okay, so if you're going to sit and you're going to watch this, I won't be looking at the YouTube chat at all. But if you look in the description, there is a link to our free trial. Now, you can get into there absolutely free, no commitment. If you cancel before the 7 days is up, then you won't pay a penny. So you can access these live classes for free all week and get involved in the chat during the live session. That's the same for biology and maths as well. So don't be shy. During the free trial, there's a link to the chemistry page in the description of this video. And of course, in biology and maths is different. And you can get the free trial for multiple subjects. So you can do biology and chemistry, biology and maths, all the different combos, all free. And you can join the free trial for a week and access all of these live classes over the next couple of weeks. So if you want to do that, you are more than welcome. So all you need to do is sign up to the free trial and head on over to the chemistry course if you want to get involved today or tomorrow or Thursday in the chemistry one. In the chemistry course on the left-hand side, you'll see live classes and recordings, and the link is in there. That's all you need to do to join the Zoom session. Okay, so I'll be chatting to the TT members in the Zoom during the live. Whenever they ask a question, I'll relay that to everybody on YouTube. But if you want to ask a question, then you're going to need to join the live class during and get the free trial to do so. Okay, or indeed you can just become a full member and pay your way. So completely up to you guys, but that's what we're doing today. So today we're going to spend I think just over an hour talking about atomic structure and all the other things that influences. So we're going to be learning chemistry today. There's not going to be any questions. There's no PDF here. Obviously, that's going to change tomorrow and Thursday. We are going to be doing some questions. So I'll be putting a PDF in the description ready for those, and you can use those. And I'll give away a few freebies, a few handy PDFs that you can only find within the TT course as well for any of you YouTubers out there. So what are we going to do today? We're going to start with atomic structure. So I'm just going to rearrange my windows here. Oh, thanks, Alex. Alex is saying that was a very inspirational introduction there. Thank you very much, Alex. Cheers, mate. So where do we start? Well, let's start with the basics first of all. Okay, I'm going to start screen sharing and share screen. iPhone, iPad via cable. Is this going to work? Yeah, it is, he says confidently. Usually I have to unplug it and plug it back in again. So just to reiterate before I start, chemistry is 11 o'clock Tuesday, Wednesday, Thursday. Maths is 1 o'clock Tuesday, Wednesday, Thursday. And biology is 5:30 p.m. Tuesday, Wednesday, Thursday. Okay, so chemistry 11, maths 1, biology 5:30. You can see the times in the YouTube and of course in the live class section there as well. So don't forget, guys, if you got any questions, just pop them in the chat in the Zoom. I will not, I repeat, not be looking at the chat in the YouTube. Just want to take notes and just watch along. That is absolutely fine. So basic atomic structure. Let's start with that. So basic GCSE atomic structure leads you to believe that we just have our nucleus and then our electrons in shells around the outside like so. But of course, now at A level, we realize that is a little more complex, shall we say. We still got protons and neutrons in our nucleus, but of course, the structure of electrons builds in a slightly different way. We do have shells, but we now refer to them as energy levels, okay? Energy levels. So as we move outwards, okay, what happens? This is a question for the Zoom chat. What happens to the energy of the electrons as we move away from the nucleus? So from energy level 1 to energy level 2 to energy level 3. Increases, absolutely. They have a much higher amount of energy. And it makes sense. Energy levels. Energy level 1 is the lowest. And of course, the outer one, the energy level 2, 3, 4, 5, whatever it might be, has the highest energy. So electrons have the highest amount of energy in the outer energy levels, okay? Increasing electron energy. So these energy levels, they don't just have electrons on rails. They're just areas where you're likely to find an electron. And they don't just live in there, and they're not all the same. Within energy levels, okay, what do we have? What do electrons live in within energy levels, folks? Orbitals, okay? Orbitals, absolutely. Some people call them subshells. That's absolutely fine, but I'm going to be referring to them as orbitals. So in our first energy level, we have an s orbital. Now, each orbital can only hold two electrons. So we put that little 2 there. So we filled this first energy level that only holds an s orbital. Shape of an s orbital, ladies and gents? Spherical. Alliteration, we loves it, okay? So an s orbital is spherical, if I can spell it. Okay, so we've got a spherical orbital, and that houses 2 electrons. So each orbital can house 2 electrons. Next up, we go to the second energy level that also has an s orbital, which can hold 2 electrons. So if we've got our first electron orbital here, our second one sits, like envelops it around it. Remember, we're talking 3 dimensions here. So that's our second s orbital. Now, also within the second energy level, we have p orbitals. How many p orbitals live in each energy level? Not quite. We're saying 6 in the chat here. There's not 6 orbitals. There are 3 orbitals, but they hold 6 electrons. I know where you're going. Just be careful. So our p electrons are dumbbell shaped or figure of 8 shaped. Okay, so we have one on the y-axis, one on the x-axis, and then I'm just going to do this as a circle because we're looking at it down the barrel of a gun, if you like. Okay, so it's like if you had 2 balloons, just put the ends together where the knots are. Okay, that's a p orbital. So what we're doing is we're looking down the two balloons like this, just from one end. Okay, so this is on the z-axis. So when they all sit together, they look like this, and this one's going from front to back. Okay, so these 3p orbitals holding 2 electrons each, and that means we can house 6 in there. Okay, so all we need to know for any specification, whether you're WJ, EdXL, AQA, OCR, you need to know this. All right, so let's build this up. So I just want you to envisage this. So this is my 1s orbital here, and then what we've got is my 2s orbital, which sits just outside it. And then we've got our 2p orbitals, which again sit just outside it, like so. Okay, so we are increasing the energy. So we not only have an increase in energy from energy level 1 to energy level 2, but we have a very slight increase in energy between the 2s and the 2p. So every time you write a big number, there's an increase in energy of the electrons. Okay, so as we're working from 1s2, 2s2, 2p6, 3s2, 3p6, we're building up the energy of electrons. The electrons within each, the energy they have is equal. Okay, so every time you write a new big number, there's an increase in energy of the electrons. So we're getting further away from the nucleus, and they have already more energy. So we get this far, 3p6. So in our periodic table, which I can whiz to on the end over here, we end up here at neon. This is our 3p6. Okay, so 1s2, 2s2, 2p6. Oh, no, and we're here. Argon, I do apologize, okay? Because what we've got so far, if I can go back to the start, I've lost my teaching board. Oop, there it is. If we go back to the start, we've got 4, 10, and we've got 18 electrons so far. So it makes sense that we are at argon, okay? Now, what happens next? What's our next orbital that gets filled after our 3p6, guys? Scarlett's saying 4s, and Christine and Charlotte and Shania, everybody's saying 4s in the chat. So that is our 4s2. It's a little sneaky one, goes in there first, and then we end up in the d orbitals, okay? So the d orbitals start at the d block here, okay? So starting with scandium, going all the way through to zinc, that's our d block. And that's because the outer electron is in a d orbital. So it gets a bit weird at this point, okay? And we can actually hold, in fact, d orbitals. We have 5 d orbitals, so that means it can hold how many electrons in total? 10, perfect, okay? So 3d10, and then we end up with 4p6. Now, this is as big as you're going to get. You are required to go up to 36 electrons, okay? That is it. This is the greatest number of electrons you'll be asked to write the electronic structure for, okay? So the 4s2 sneaks in before the 3d, and that makes sense because these two here, potassium and calcium, this is 4s1 ending in 4s1 for potassium and 4s2 for calcium. Makes sense because they're before our d block, okay? Now you can write 3d10, then 4s2 if you really want to. But my advice is, so you don't forget, 4s2 goes in before the 3d. They'll accept them either way around in all honesty. But in real terms, 4s electrons have slightly lower energy than 3d10 electrons, okay, or 3d electrons. So just be wary of that, folks, okay? So when we're building our electronic structure, this is what we need to do. We start at the lowest energy level and work our way up. Now, it's the last thing I'm going to say about building atoms, because I know we've all done this, year 12 and year 13, is the last thing is going to be electrons in boxes, okay? So we've got these electrons in boxes. Each can hold 2 electrons like so, okay? And this is a 3p orbital. So don't forget, we've got 3 orbitals. That's 3p6. This is 1s2, 2s2, 2p6, 3s2, 3p6. Now, how do we fill these boxes? Well, there's something called Hund's rule. So they fill up that s orbital like so, Same here, they haven't got a choice on where to go. They have to fill that s orbital first. Now we get to the 2p6. So this one goes in there. Now, do we pair up or does it go in the next orbital? Pair up or next orbital? That's my question. Perfect. Next orbital. Good. Because electrons are negative. You put two negative things next to each other, they're going to repel. So when you're filling these orbitals, it's really important when you get to the p orbitals that you go 1, 2, 3, like so. Okay, they fill up individually and then they pair up. I'm just doing this in another color just to show you. Okay, that's really, really important. It's called Hund's rule. And my analogy is when you get on a bus, not that many of us have been on a bus a lot recently, but when you get on a bus and you see some people sat in some seats on their own, okay, what do? Do you go and sit next to that person, even though there's a whole bus of empty seats there? Or is it our natural inclination just to go and find an empty seat and sit on our own? What are you going to do? Okay, you're going to sit next to that one single random stranger on the bus, even though the rest of the bus is empty. You might get a few funny looks, mightn't you? Okay, so of course, you just need to think, getting on the bus, I'm going to sit in the empty seats. It's your natural inclination, and it's the same for electrons in boxes. Hund's rule, don't forget it. So filling in individual orbitals first, then pairing up, and it's the same when you get to the d orbitals as well. So really, really important. So that's filling electron orbitals. Now, let's not forget, what we've got here is a load of forces acting on each other. We've got a positive nucleus. Okay, I'm just going to shade that in. And then we've got our energy levels going around it. Okay, you'll only ever be asked to draw the energy levels like this. Oh, what's the thing where S fill up first and empty first? Oh, yeah, so we're talking ions there. So Scarlett's asking what happens when the S fills first, but then it gets emptied first. That's with transition metals. We're going to get to that in a second, okay? It's when we're forming ions. So let's have a look at the forces acting. So the forces acting on that positive nucleus and our 1s2 electrons are really, really strong. Why are they really strong? Why is that positive nucleus really attracted? Or why are those electrons really very highly attracted to that nucleus? Good. They're really close. And what else? No shielding is the answer in the chat here. Brilliant. They're close and there's no shielding. Now, shielding is, of course, where you have full energy orbitals, full electron orbitals between the outer one and the nucleus. Okay, I always think of shielding like this. So you got two bar magnets, north and south, they're attracted to each other. You put them close together, you can feel that attraction between the north and south and a bar magnet. However, if you put a big thick book between them, like shielding, okay, then the attraction between those two magnets isn't so much anymore, okay? So just think of it like that, okay? North and south in a magnet, the closer they are, the stronger the attraction. But if you put things between them, like full energy levels of electrons, that attraction is going to weaken. So we add another energy level here with our second energy level electrons. These are our 2s and our 2p, all put together in one shell, old school like GCSE. Now, of course, this is going to be a weaker attraction between those and the nucleus because of they're further away. And there is one lot of shielding. There's a whole energy level between those electrons and the nucleus, okay? So absolutely, as you get further away from the nucleus and you get more shielding between those electrons and the nucleus, that means your attraction between them is less, okay, is absolutely less. So the higher energy, they're further away from the nucleus, and there's a weaker attraction between them and the nucleus as you get further away. All these things are gonna come back later on, all right? Really, really important. So we know how to build an atom now. I'm just gonna take a quick drink. Any questions so far, guys, in the chat? So question is from Scholar. If there are more electrons in a shell, can it become weaker by opposing the electrons they're near in that shell? So we do get some repulsion whenever you pair electrons up, like we've done in this 2s2 orbital here. There is some repulsion between them. But we don't really need to take that into account unless we're talking about something very specific, which we will get to in terms of ionization energy. So you do have repulsion between them, but the force of attraction between those electrons in a nucleus is much greater. And, you know, that's why they stay in place, if you like, okay? So we'll talk about repulsion between paired electrons shortly. I promise you that, okay? So what are we going to talk about next? Let's have a look at some, I would like to think, fairly obvious stuff. So atomic structure and the forces acting within atoms and between atoms and stuff like that are really, really important. Shania, why is the repulsion in 2p significant but not in 2s? I will get to that. We're going to talk ionization energies, I promise, and we will get to that, Shania. I'll explain that, okay? So let's have a look at how building atoms can actually influence what's going on in the periodic table and the trends in the periodic table, okay? So let's head on over to our periodic table. I'm going to get rid of this shizzle. Okay, so I'm going to look, let's use red because we can see it properly. Okay, so as we go down a group, any group, bearing in mind how we're building our energy levels, what happens to the radius, the atomic radius of the atoms as you go down a group? Increases, absolutely, okay? So this is just the outer energy level only. So as you go down, we're actually building in size as we go down. The reason, I've seen this in an exam paper. Why does atomic radius increase down a group? Literally, we're adding an energy level each time we go down a group, okay? Because the group number tells us how many energy levels we have, okay? Or how many energy levels are occupied by electrons, okay? So of course, this is our, well, hydrogen's 1s1, isn't it? Lithium is 2s1, 3s1, potassium is 4s1, rubidium will be 5s1. So they're all in the S block, aren't they? And we're going to get to that in a second. What's more disconcerting, if you like, is the trend across a period. So what happens to the trend in atomic radius going from left to right? Good, decreases, okay? So what we actually see here, I'm not going to do all of them, but we see a slight decrease. So if this is lithium, okay, then we get smaller and smaller and smaller. It's not that, you know, it's not that extreme, but they do get smaller. The atomic radius gets smaller. What's our reason for that in the chat, please, guys? Why is it, even though we're adding electrons, our atomic radius gets smaller? Why is that? Good. There's a few parts to this answer, and this is a stock answer if you want to write this down, anybody in YouTube as well. So an increase in nuclear charge. Okay, so obviously we're adding a proton, lithium 3, beryllium 4, boron 5, all the same shielding. So we're not same, you can say same shielding or all electrons added to same energy level. EL is energy level. Excuse me a second. Just turn Alexa off. She's listening in. So increase in nuclear charge, no increase in shielding. Electrons are pulled closer to the nucleus. Absolutely. Thank you, Alex. And I'm sure other people said that as well in the chat. So electrons more tightly held or closer to nucleus. So greater attraction, and that means they're pulled in closer. And that's the same for any period, okay? So period 2, period 3, period 4, it's the same. So knowing your atomic structure helps you deduce the atomic radius, okay? Really, really important. So what about ions? Okay, so making ions is really, really important, okay? Or being able to deduce the formula of ions. So when we're forming ions, I'll just go back to this. Okay, what's the general rule? How do you know, let's say for group 2, that it's a 2+ charge? What electronic structure are you aiming for? If you are asked for the electronic structure, let's say of, I don't know, Be2+, for example. full outer shell of electrons is the answer, and you'd be absolutely right. So they have, so ions always have, or the most common ions, same electronic structure as the nearest, can't spell, noble gas. Okay, so it's the nearest noble gas. Now, obviously, you know, within the middle of the periodic table, it gets a bit more iffy, shall we say. But what we can rely on is for our group 1, group 2, group 3, okay, and of course, you know, groups 5, 6, and 7 as well, we actually get the nearest noble gas, okay? So let's say for magnesium, whoops, it's all moving. Let's say for magnesium, okay, we know it's going to go to its nearest noble gas, which is neon, okay? So it loses electrons, so -2 electrons, and we end up with the same electronic structure as neon, so a full outer energy level. That's really, really important. What is the term that we use to say, okay, these two things, so like Mg2 plus and neon, they are what with each other? Boom, isoelectronic. Okay, so that means they have the same electronic structure. The number of protons and neutrons they have is, of course, different, okay, because it wouldn't be magnesium and it wouldn't be neon otherwise, but their electronic structure is the same. They have the same number of electrons and they're arranged in their configuration in exactly the same way, okay, really, really important. Question, when writing electronic structure, do we need to know how write is in shorthand using noble gases, e.g. AR and then the rest? Okay, so Scarlett's question, could you put, let's say, neon and then 3s2? So if they ask you for the shorthand, then write the shorthand. But most of the time, I don't think in the new spec I've seen one, to be honest with you. They always ask for the full electronic configuration. So if you do cheat, not cheat, but you know, use the shorthand, then they won't give you the mark. So if they ask for the full electronic configuration, you start with 1s, okay, and then work your way forwards from there. You need to do that. So isoelectronic. So can anybody tell me, please, what else would be isoelectronic with neon? And I'm going to write them down as they come through on the chat, guys. So what other ions would you expect to be isoelectronic? Good. O2 minus, F minus, good. Any more for any more? N3 minus, absolutely, okay. A nitride ion, N3 minus. Al3 plus, good, I like it, okay. Even aluminium from here loses 1, 2, and 3 electrons and ends up at neon. Na plus, good. And of course, we've got Mg2 plus there as well. Now, if you could have Si4 plus, then it would be the same, but it tends not to form that SA4 plus ion. It's a common oxidation state, but it tends not to be ionized to 4 plus. Although technically, yes, I'm going to give you that, David, okay? Si4 plus there. So isoelectronic is really, really important term to help you figure out what the charges on these ions are. But of course, you know, knowing the general trends, group 1, 1 plus, group 2, 2 plus, group 3, 3 plus, group 5, 3 minus, like phosphorus and nitrogen. Group 6 is 2 minus, and of course, group 7 is 1 minus. So don't forget, they're all isoelectronic, same electronic structure and configuration. Now, one thing I want to mention are these bad boys here, okay, are D block elements. Of course, if they're in the D block, that means that outer electrons are in a D orbital, in which case, and we don't ever really focus on the 3D ones here, okay? So in period 4, it's the 3D. No, it's a bit confusing, but it's the 3D that we focus on. Now, when we're removing electrons from those, let's say from, let's do V2 plus. Let's do V2 plus. So vanadium is 23. Okay, so I'm going to write out the electronic structure for vanadium. Okay, so let's do V3 plus, sorry. So that's 1s2, 2s2, 2p6. That's 23 electrons. 3s2, 3p6, 4s2, 3d watt, ladies and gentlemen. 10, 20, 3D, not 0. Well, no, we're just going for V, sorry, to start with. I'm just going to show you how they get removed. Yeah, 3D3, good. So that is vanadium. Now, don't forget, when we are forming ions with our transition metals, with our D block metals, okay, we said 4s gets filled before 3D, which is absolutely true, okay? Good, you're already on it in the chat and the Zoom, guys, what I'm about to say. So 4s2 get put in first. So in terms of 4s, first in, first out. So when you're forming ions of not noble gases, but transition metals, 4s electrons are put in first, but they're also the first out. So V3 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 4s0. You can or cannot put that in there. They won't mark you down if you do or don't. And then 3d2. Okay, so that will be our 3 electrons. We've taken the 2 from the 4s and 1 from the 3d. It is not, if I can just copy this and paste it because it's quicker, he says confidently. There we go. It is not 4s2 3d0. It is not that. Okay, so you do not take your 3d electrons first. You take your 4s electrons first. Okay, so 4s electrons, when it comes to transition metals, first in, first out. Okay, always remember that. It should come in really, really handy. And one last thing I will just mention is that I'm sure you're all aware that chromium and copper just ever so slightly different in terms of their electronic structure. But when you're forming ions, okay, it works in exactly the same way. 4s electrons out first, then your 3D, all right? So OCR people, you'll never get asked about those, okay? So in the spec, it actually says you will not be asked about the electronic structure of chromium and copper. But for the rest of you, you absolutely need to know it. OCR do not need to know that, okay? So those are an exception to the rule in terms of building our electrons, but they fall in line when removing electrons to form ions. Really, really important that, okay? So we have spent 20 minutes or so talking about electronic structure, forming ions, and finding our way around the periodic table, okay? All of that really, really important. Let's get into some nitty gritty. Let's get into some other chemistry and how electronic structure influences, and actually more than influences, dictates some of the other things that we see in A-level chemistry. Excuse me. So what's next? Well, I think a logical place to go is this. Ionization energies, okay? So first, ionization energy, okay? Well, there is a definition that goes with this. This is really important, the definition, because if you know the definition of pat, then you can write an equation for it, okay? So it is the energy required, excuse me, while I'm writing, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, okay? And you could put on the end there, forming 1 mole of gaseous 1+ ions, if you really wanted to, okay? But the first bit is the most important. So the energy required, or the enthalpy change that happens when you remove 1 mole of electrons from 1 mole of gaseous atoms. This is important. Is it an endo or an exothermic process, this? Endo, good. Always positive delta H values, okay? So it's an endothermic process. We need to put energy in to remove electrons. Remember, they're trying to rip them away from that attraction to the nucleus that they have, okay? So the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So we have 1 mole of gaseous X, whatever that is, and that goes to X plus gas, and then there's your electron that you've removed. Really, really important, okay? So first, ionization energies. Now, let's not forget, we need to give electrons, when we're ionizing an atom, we need to give one of those outer electrons enough energy so that it actually gets removed from the from the atom completely. Okay, so we've got our atom here, and I'm just going to do a mock-up of one. Okay, that's our electron, let's say we are trying to remove. Now, remind me again, what happens to the amount of energy electrons have as you get further away from the nucleus? It increases. Absolutely, it increases. So think of it this way. You're trying to get the electrons to a set amount of energy, the bar, okay? Think of it as a bar. So the further away electrons are from the nucleus, okay, the more energy they've got anyway. So all you have to do is just give them a little bit more energy to get them over the bar. The ones lower down, you have to give them quite a lot of energy to get over that bar, okay? And then they're off, okay? Alex, question. My teacher said that ionization energies in relation to periodicity will be on my exam. What does this mean? Trends in periodic table. Yes, absolutely. Okay. So we're going to cover all of that, Alex. Okay. Just by chance, we're going to be covering all of that and linking it to the periodic table and stuff, pal. Okay. So I want you to have that vision in your head when it comes to ionization energies. There's a bar. You need to give electrons enough energy to get over that bar, and then they're gone out of the atom, and it's been ionized. Okay, so why does energy increase? Well, that's more physics than chemistry. Okay, so it's a very good question, Saba. Why does energy increase? All we need to know at A level, it just does. Okay, so it's a great question, but we're not going to muddy the waters with that today. Okay, if you want to look that up in your own time, you'll end up on some physics websites, then that's fine. So we're looking to ionize an atom. So let's have a look. I think it's probably more important to have a look at the trends first, okay? So let's have a look at our first ionization energy, okay? So this is atomic number down here, okay? So this is, of course, hydrogen, and then moving forwards. These are the first IEs, okay? So how can we spot where our noble gases are? There are 3 noble gases in this graph. Where are they? Good, Yasmina, the peaks, or Yasmina, I do apologize, the peaks, absolutely. So we have got helium, we've got neon, and we've got argon just here, okay? So they are our peaks. That's really, really important. So noble gases, and this helps you when you get to exams, just recognizing these trends equal the peaks. Now, what are the troughs down here, guys? These 3 bad boys, what are they? Group 1s, absolutely, okay? So group 1s equals the troughs, okay, the ones at the bottom. So this would be lithium, sodium, and potassium. Okay, lithium, sodium, potassium, they're our alkali metals. So that, as a kickoff, is really, really helpful. Okay, really, really helpful. So why do we get, first of all, this decrease here? Why is there a massive decrease between helium and lithium? Increase in atomic radius. I'm going to write this down. Okay, so from helium to lithium. So there's an increase in atomic radius. Increased shielding. Good. I'll show you a picture of this in a sec. We're going into a new energy level. Good is another way of putting it. So we've increased the shielding, therefore we must be in a new energy level. Increase in atomic radius. Shielding from s orbital, new energy level further than, yeah, we're all saying the same things, absolutely. Because if we've got helium and we're just trying to remove this electron here, but then we go to lithium, oops, too big, and that's our 1s2 orbital. And what we've got here is we're trying to remove this electron. So we've got increased distance, increased shielding, therefore it's much easier to actually remove that further electron, okay? So what I wouldn't do when answering questions like this is reference any orbitals in any way, okay? I will tell you when we need to talk about orbitals, but whenever you're answering just general questions about ionization energies, you're using all these key phrases. Now, of course, in the video in the course, I give you a stock answer for your exam board for this, okay, which is really, really important. So go and check that out. So increased atomic radius, the outer electrons further away, in other words, from the nucleus, okay, so increased distance. So I could just put that there. We're basically saying the same thing. And then, of course, because there's increased shielding, there's shielding from the first energy level between the nucleus and outer electron. So therefore, it's a lot easier to actually remove it. Okay, and it's the same answer. You can give that stock answer for why is sodium lower than neon, why is potassium lower than argon. So you can give that stock answer for any of those trends. Okay, really, really important. So when you're going down a group, when you're going down a group, any group, oops, excuse me, I'll get rid of all this again. I don't really want to delete that. So when you're going down a group, any group, if they ask you, why has francium got a lower first ionization energy than cesium, okay, then you can give that stock answer. Why has bromine got a lower first ionization energy than chlorine? Why has calcium got a lower first ionization than magnesium? You can just give that stock answer and you'll get all the marks, okay? Really, really important. Of course, if they ask the flip, okay, so why is cesium higher than francium? Why is magnesium higher than calcium? And so on and so forth. You just need to flip your answer slightly, okay? But word to the wise, in terms of exam technique, they will always, as long as you give a correct answer, if you give like the flip answer to it, the inverse answer to it, then they will credit you with the marks, okay? So if they asked you, why has francium got a lower first IE than cesium, and you started saying, well, cesium, there's less shielding, therefore, and less distance between the electrons and nucleus, and therefore it's a stronger attraction. You're answering it kind of in the flip way, aren't you? But you will get the marks. But my advice, because the examiners, of course, are using the mark schemes, and that's what's in the mark scheme, try and answer it in the context of the question. That'll be my advice to you, okay? So that's down a group. Now, across a period, we, of course, have a very clear trend, okay? And the general trend going across a period is that it increases, okay? Now, we said before that atomic radius decreases as you go across a period because of an increase in nuclear charge, okay? Holding those electrons in more tightly. That would actually answer why we get this general increase going from left to right across a period. Why do we have a general increase? Stronger nuclear charge, no extra shielding, electrons are held more tightly or stronger attraction to the nucleus. Same answer, different question, okay? So that's why I want to do this today. We're making all these links together. So going from left to right across a period, increased nuclear charge, no extra shielding, and of course, the distance decreases. So there's a stronger attraction between the outer electrons and the nucleus, and that's why that first ionization energy increases, all right? However, ladies and gentlemen, and notice how we haven't mentioned a single orbital in any of those answers, all right? Really important that, because orbitals do not figure at this point. Yeah, exceptions, absolutely. Thank you, Shania. So what we need to talk about next are these exceptions to the rule, which are here and here, okay? Now these are, and you can spot them really easily, okay? Beryllium and boron, and these are nitrogen and oxygen. This is magnesium and aluminium, and this is phosphorus and sulfur, okay? So they are your exceptions to that increase growing across a periodic table. And that's why we need to talk about orbitals. And this is the only place you mention orbitals, folks. So there are two pairs here, and they're not the obvious pairs that you think. We are not pairing them like this, okay? We are pairing them like this, okay? Now, there's a reason for that, because we're going from, so beryllium to boron and magnesium to aluminium, we're going from group 2 to group 3, okay? We're just dealing with a period down, okay? That's all we're doing, okay? So beryllium and boron, they sit directly above magnesium and aluminium. So in the chat, please, guys, give me one sentence for part of your answer. If I asked you, why is boron I should put boron there. Why has boron got a lower first ionization energy than beryllium? Give me one sentence you would put in your answer that would make up part of maybe like a 3 marker or something like that. Anything in the chat. Why has boron got a lower first ionization energy than beryllium? Because you'd expect it to be higher. Different orbital, electron pair repel, paired electrons repel each other, s electron shields p orbitals. So we've got a mixture of answers here, and I will say that if you mentioned that the s orbital shields the p orbital, you'd be absolutely right. Beryllium is 1s2, 2s2. Boron is 1s2, 2s2, 2p1. Okay, so what we're doing here is this electron here is easier to remove than this one. Okay, so the reason for beryllium to boron is that the boron electron has been removed from the 2p orbital, which is shielded or which is further away. So increased distance ever so slightly, okay, because we're still working within the same energy level, and it's shielded by the 2s orbital. Okay, so therefore less energy required to remove it. Okay, so we're talking about these bad boys here. This is about shielding. Okay, so they're both about shielding. Okay, of course, if we were answering the question for magnesium and aluminium, you'd say the 3s and the 3p orbital, not the 2s and the 2p. So it always pays to be specific. All right, so you talk about orbitals for those exceptions. Now, what about our other exception here? Okay, our other exception, of course, is between nitrogen to oxygen and phosphorus to sulfur. Good. You're already anticipating my question in the chat and the Zoom, guys. So electron pair repulsion here. Okay. So of course, let's do it for phosphorus and sulfur. Okay. So phosphorus ends in blah 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 blah. So that will be 1, 2, 3. So that would be 3s3. So 1, 2, 3. Okay. So that will be phosphorus. Our sulfur is 3s4. So 1, 2, 3. Remember getting on the bus? 4. So this electron here. So in fact, what I'm going to do is I'm going to highlight the electron that we're removing in red. That's the one we're removing from phosphorus. This is the one we're removing from sulfur. Okay. So you would expect sulfur to have a higher first ionization energy. It doesn't. It has a lower one. You think more neutrons, electrons, more attracted to the nucleus. It must be harder. No. Remember what we said before. Paired electrons within an orbital do have repulsion between them. Okay, they're both negative. Of course, they're going to repel each other. So what we need to say here that sulfur has a pair of electrons in a 3s orbital. Okay, repulsion between these means less energy is required to remove one. Okay. Yeah, sorry. I'm talking S, I mean P. Thank you very much. All right. Talking and writing at the same time, you'd think it'd be a really important skill. And it is a really important skill for a teacher. But sometimes my brain just kind of wanders off. All right. So yes, 3p. I do apologize. Thank you very much, guys. So in our p orbital, 3p orbital, there's repulsion between two electrons. And of course, that means they're easier to remove. Now, remember what I said before about this bar. We're trying to give electrons enough energy to get over this imaginary bar to be ionized. If you've got a pair of electrons that are next to each other and they're repelling anyway. And like, so imagine again, two people sat on a seat, right? You're trying to remove one person from the seat next to the other one, okay? And they're not willing to move. But if that other person sat next to them starts giving them a push, then it's going to be easier to remove that person from the seat, isn't it? Okay, so just think of it that way. And maybe scraping the barrel of that analogy a little bit, okay? But you get what I mean. So, Shania, aha. So, isn't there repulsion in the 3s2 as well? There is, Shania, but because there's no other option. So, in an s orbital, you only ever get a singular s orbital, don't you? Okay, so once you get to that s orbital, you've taken away all the p's, for example, and you get to the s, you'd think this one would be lower than that one, but it's not. Okay, so because there's no other option, it's just the way it is. Okay, it does get increasingly more difficult to remove an electron. We've seen successive ionization energies. So this is, as you're working your way down, it is naturally easier to remove that than the next one. Okay, but when it comes to removing them, let's say you're going from magnesium to sodium, it's not easier for magnesium. I see what you're saying. Okay, I see what you're saying. It must have something to do with the way the orbitals are arranged. I don't know the answer to that. It's a very good question, but not one you need to know the answer to. Okay, I see what you're saying there, actually. So yeah, why is it when you get to a pair in a p orbital, you get that dip, but we don't get it between groups 1 and 2. We don't get a dip there. That's a very good question. I've never been asked that before. And you know what? I've never even thought about it, Shania. So if you want a bit of extra homework, not that you need it at the moment, but you'd be my guest to go and check that out. Okay, it's probably a physics thing again, to be honest with you. Okay, so ionization energies, really, really, yeah. Yeah, I'd rather not as well. Ionization energy is, of course, really important. Stock answers, really important, okay? So have four stock answers at the ready for your ionization energies. Down a group, across a period, your exceptions between groups 2 and 3, and your exceptions between groups 5 and 6, okay? Really, really important. And again, within the course, specific to your example, based on the mark schemes of the exams, I've written those rules as well. They are slightly different for each exam board, but essentially amount to the same thing. Okay, but watch the content guide video on that in the course. So knowing your electronic structure is really, really important. And in fact, when we get to successive ionization energies, then of course, your electronic structure comes back to remind you what it's all about. So if we just pick an element, let's pick magnesium. Okay, so we're looking at the first to the second to the third successive ionization energies of magnesium. Now, what students get wrong with this a lot of the time is they work from the inside out, not from the outside in. Of course, when we're removing electrons, we start with the outermost electrons and work our way in. So that's really, really important. So what I would do if I was asked to kind of draw the graph for the successive ionization energies of magnesium, I'd write out the electronic structure. So 1s2, 2s2, 2p6, 3s2. Okay, so we've got 12 electrons there, really, really important, but we're starting with our s2 electrons. So lowest energy first, then we get a little bit higher because we've lost an electron. We've got an effective positive charge now on our entire atom, so it gets more difficult to remove, even though we're working within the same energy level. So that's our 3s energy level done. What happens next? What happens with our third ionization energy, successive ionization energy? Huge increase. We get a massive jump. Thank you very much, those of you in the chat. So we do get a massive jump to our third, and then we just get a gradual increase. Again, 1, 2, 3, 4, 5, 6. So that's our 2p6. So we're working within the same orbital there. What about the next two? Small increase. Some of you are saying there's a big jump here. There's not. The reason that we're going to, just carrying on the trend here is because we're still working within this second energy level. So you know what? Orbitals, as far as we're concerned, in successive ionization energies, don't play a part. So your hang on a minute, third, fourth, fifth, sixth, seventh, eighth, your ninth and 10th will still be on this same trajectory, if I can say that. Okay. It's only when you get to the first energy level that we get another jump for our 11th and then our 12th. Okay. So what we end up with is this big jump, big jump. Okay. So when we're looking at successive ionization energies for atoms, it gives us information about the electronic structure. Okay. Because the big jumps, where we have that big jump, because we're going down to the next energy level, closer to the nucleus, less shielding. Okay. That means it's going to be much, much harder to remove that next electron from the next energy level. Okay. Now, the way to remember this in terms of, because they always link it to groups and stuff. We've probably all seen these tables of just numbers and you're looking for the big jumps between the numbers. Typical question, right? So what you're looking for is if there's a magnesium's in group 2, right? Where's our big jump for magnesium? Our first big jump for magnesium? 2 to 3. Okay, so group 2, there's a big jump between 2 and 3. If you had a group 3 element, there'd be a big jump between 3 and 4. If there's a group 4 element, there's a big jump between 4 and 5. Notice, I don't know what the number equivalent of alliteration is, but notice that, okay? Group 2, big jump from 2 to 3. Group 3, big jump from 3 to 4. Group 4, big jump from 4 to 5, and so on and so forth, okay? So it's just the way it works out. Once you've removed those first lot of electrons from the outer energy level, then you would have a big jump, okay? So last one, for example, if we were to take a neon, for example, okay, we'd have 1, 2, I'll do it a bit higher. 1, 2, 3, 4, 5, 6, 7, 8 before we get a big jump to the 9th, because you're removing 8 electrons all from that second energy level, and then you get a big jump between the 9th and then to the 10th. Okay, that's it. Yeah, first ones from the outer energy level, and the group number. As you go down, you're taking away electrons from closer and closer and closer to the nucleus. And of course, you get a big jump when you go down to the next level, and then a big jump when you go down to the next level. Okay, so that's what we're on about. Just remember this kind of link between looking for your jumps. Okay, so just remember that. Really important, that one. Now, moving on. We are moving on from ionization energies. Remember, we've got a lot to cover today. We're going to look at some more periodic trends, all right? So atomic structure. I want you to remember it's all about atomic structure, folks, okay? So, excuse me while I'm having a bit of a rub out here. Okay. Down group 1, GCSE. What happens to reactivity as you go down group 1? Increases, okay? So increasing reactivity. Now, at A level, we shouldn't really use the term reactivity anymore. It's a bit vague. It's a bit of a dirty word, to be honest with you, okay? Because what does that mean, okay? And what type of agent is it? Is it acting as an acid? Is it a really reactive acid? Is it an oxidizing agent? Is it a reducing agent? Blah, 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 blah. Alex has already preempted my question. The reason why we have an increase in reactivity is that that outer electron is easier to remove. Why? Because they're metals. They lose electrons when they react. We go to Li+, Na+, K+, and so on and so forth. The further we go down, the bigger the atomic radius, the further away that electron is, the easier it is to be removed, okay? So again, we're looking at atomic structure to give us a reason behind it. I'm going to get rid of this word reactivity here, okay? Now, in terms of redox, what are these, okay? Increasing watt power as we go down the group, increasing watt power, reduction power, or reducing power or oxidizing power. They're being oxidized because they're losing an electron. So they are what? reducing agents. So you get an increase in reducing power as you go down group 1 and group 2, okay? Because they're losing electrons themselves. They are being oxidized themselves. All right, get started a little scroll, mate. Here we go. They're being oxidized themselves, so they are acting as reducing agents. So the reducing power increases down the group. The reason: outer electrons further away from the nucleus, increased shielding, less attraction to the nucleus. Therefore, it's easier to lose that outer electron, which is why francium just blows its top anytime it's exposed to any amount of moisture in the air. Okay, it's just, I'm FR plus now. Okay, so it loses those electrons really, really quickly. Now, what about over here? We're going to ignore the noble gases because, of course, they've got full outer energy levels. They tend not to be reduced or oxidized in any way for the most part. But what about going up group 7? What can we say about what's the trend there? Keep it in terms of redox, folks. Good. Thank you, Alex. So as you go up the group, you get increasing oxidizing power. Okay. Now, the reason here is the same but different. Okay. Fluorine, okay, remember, they have to attract an electron towards them. Okay. They are being reduced themselves. So we could say the inverse answer to that, Ellie, absolutely. So as you go down group 7, you could say decreasing oxidizing power. That is absolutely fine, okay? But whatever you do to remember the trend is really important. But what I'm saying here is if you understand atomic structure, you don't need to remember the trend. You can work it out in your head. So it's like, okay, which is the strongest oxidizing agent between fluorine and chlorine? I don't know which one's the strongest oxidizing agent. Well, fluorine, smaller atom, okay? You've got electrons closer to the outer electrons are closer to the nucleus, increased attraction to that nucleus. So any passing electrons, okay, so you've got a fluorine atom here, any passing electrons are going to be like, whoa, just drawn in by that low shielding, low distance between the outer energy level and nucleus. And therefore, it's really good at taking electrons from other things. So it's got a really high oxidizing power, okay? F is the strongest oxidizing agent. Yeah, absolutely. Okay. So because it's got a small atomic radius, okay, the nucleus is really good. There's a strong attraction to the nucleus and outer energy level where that electron gets added to the outer energy level. Okay. Now, if you look at iodine down the bottom, you got your nucleus here. There's a massive distance. Any electron that's traveling past, iodine's going to be like, I just haven't got the energy to actually attract that electron. So iodine's not a very good oxidizing agent at all because it's not very good at attracting electrons. Oh, Scarlett saying, can we link this to electronegativity? Yes, we can. And that's exactly what we're going to be doing in the next section. It's like you reading my notes here, Scarlett, all right? Just stop looking at my notes. So oxidizing and reducing power, even if you can't remember the trend, you know atomic structure, you know how they're built, you know about shielding and distance from the nucleus and all that. You can rely on that to work it out. That's what I'm saying. Now, another thing, and this is a section of the course that a lot of people get a bit kerfuffled by, okay? So let's say in group 7, we have got fluorine, chlorine, bromine, iodine. We don't ever bother with astatine. I don't know why. Like, we just don't talk about astatine. It's like the weird uncle at the wedding nobody really talks about, but it's there. So anyway, I know, poor astatine, right? So, but then we've got F minus, Cr minus, Br minus, and I minus, okay? We've already established that these are oxidizing agents, okay? Fluorine being number 1, number 2. I'm going to rank order them, okay? So this is the, that's the strongest oxidizing agent, fluorine, okay? So if the halogens are oxidizing agents, Yasmina, you guys in the Zoom chat, you're just taking words out of my mouth now. Halides are reducing agents. Okay. Now, just because something has gained an electron doesn't mean, or lost an electron, doesn't mean the opposite can't happen. It can't just take it back or give it away again. Okay. Really, really important. So bearing in mind ionic radius here, okay? And let's say this is the one electron that they've just gained from somewhere else. I'm not going to draw them all out. Which of those would be the best at actually giving an electron away? Iodine, okay? So iodine is the strongest reducing agent, bromine, then chlorine, then, iodide, bromide, chloride, then fluoride, okay? So it's the easiest to lose an electron. Why is it the easiest? Why is it that I minus loses the electron the most easily? Good. Increased shielding, increased distance, okay? Weaker attraction, okay? So if something comes along and iodine's had that extra electron from somewhere, and iodide is like, I'm happy, I got a full outer shell, I got that extra electron from somewhere, and then something comes along and says, I'll have that. Iodine's just like, it just flakes under the pressure. It's like, yeah, okay, fine, whatever, have it, okay? So in actual fact, it's a very strong reducing agent, okay? Iodide, okay? But of course, fluoride, not so good, because once it's got that electron in its grasp in the outer energy level, because it's close, because there's no little shielding, okay? Because there's a strong attraction between the outer electrons and the nucleus, it ain't letting go, all right? So it's going to take a hell of an oxidizing agent to actually take that electron back off fluoride, okay? So when you get those questions about like those redox or displacement reactions between halogens and halides, just remember that. And even when it comes to, and who doesn't need to know this, OCR doesn't need to know this, but the reactions between sodium halides and conch sulfuric acid. The reason why is it you get more of a reaction when it comes to sodium iodide than you do for sodium bromide? Why does that redox reaction happen more? Okay, yes, OCR are very lucky that they do not need to know that. So again, if you get those questions, it's all about atomic structure. Why does iodide reduce sulfur more than bromide does? Well, because it's a stronger reducing agent. The reason, because it's got more shielding, greater distance between the outer electrons and nucleus, therefore it loses that electron more easily and reduces sulfur more easily, okay? So all of this, okay? So Yasmina, so S goes all the way down to -2 because iodide is such a strong reducing agent. Absolutely, okay? And again, it's all down to atomic structure. Massively, massively important, okay? So don't forget, if you get those questions, yes, you have to remember the equations for that. I'm not going to get into it because, yeah, you don't deserve that in the, well, it's PM now, but anyway, lunchtime. But just remember, if you're asked to explain why you get a more reduced version of sulfur with iodide, VD, bromide, and so on and so forth, then that's the reason, okay? Fluoride and chloride, you don't get a redox reaction at all. They're not strong enough reducing agents to reduce sulfur at all. You just get an acid-base reaction there, okay? So that's a really important. So again, it's another link between atomic structure and something else in the spec that you thought had nothing to do with it, okay? There is a video, Shania, in the content guide for all the equations you need to know for those reactions with conch sulfuric acid, okay? Mez, it feels so nice when everything makes sense. I appreciate that. Thank you so much, mate. And it's these links that we never really take the time to make because there's just not enough time, and especially this year where you and your teachers have been so up against it, okay? So I'm loving that you like this. I'm loving that you like this, okay? You are the master of the atom, Anch. You are indeed, okay? Monica, I'm so pleased that you're liking this, okay? That's great. Just checking in on YouTube. Anybody in YouTube want to post something? I'll have a quick look over there, see how you guys are getting on. Is everything making sense over there in YouTube, folks? Great. So we haven't finished yet. We haven't finished yet. I'm going to take another sip and we're going to crack on. So next up, another trend in the periodic table that, of course, we can link to atomic structure. And it is this. Who mentioned electronegativity before? Nobody owning up? Anyway, somebody mentioned Meg. Was it Meg? All right. So electronegativity. What are our top 3 highest elements with the highest electronegativity? Nof. Absolutely. Okay, it's these bad boys here. Okay, so highest electronegativity over here. Why do they have, oh, sorry, first of all, what is the definition of electronegativity? I won't get you guys to type it, but is the ability of an atom to attract a pair of electrons in a covalent bond. Okay, so when you've got two atoms that are the same, those two electrons that are being shared are shared equally. Okay, they play nice, they share them equally. So there's a reason why these have high electronegativity. And the reason is, high charge density is a good way of putting it. It's another way of saying high nuclear charge, small atomic radius, low amount of shielding, high attraction between the nucleus and outer electrons. All of those things that we know and love from ionization energies, from explaining redox and reactions and stuff like that, and atomic radius, all of those things come back again. Fluorine is more electronegative than oxygen. Why? Increased nuclear charge, increased attraction to outer electrons. Therefore, it's going to attract the bonding pair of electrons a lot more than oxygen is, which is more than what nitrogen is, which is why we end up with this trend of increasing electronegativity going basically from bottom left to top right. Okay, this is the daddy of electronegativity up here, the fluorine atom. Okay, so nitrogen, oxygen, and fluorine way above the rest. Okay, down here, not so much. They're quite highly electronegative, but they've got that extra shell of electrons. They've got that extra full energy level of electrons, which means increased shielding, less of an attraction between the nucleus and outer energy levels. So don't get me wrong, they are electronegative and they will attract a bonding pair of electrons towards them. But here, nitrogen, oxygen, fluorine, high electronegativity. And this is how we end up with polar bonds in covalent substances, okay? Because if we've got something like methane, okay, and then we compare to something like fluoromethane, yes, we've got slight differences in electronegativity across those bonds there, but overall, it's neutral, okay? There's no clear positive and negative end. Whereas here, this is delta positive and this is delta negative. Why? Because fluorine, okay, hogs that pair of electrons that's bonding between them, okay? So we end up with a permanent dipole here. Okay, so permanent dipole here because of that high electronegativity. And because fluorine has such a high electronegativity, that's why we get the permanent dipole. So atomic structure, okay, let me write this out for you. So atomic structure, that dictates how electronegative an atom is, which then dictates what sort of polar bonds that we have, which then dictates what intermolecular forces a molecule has. Okay, so yes, sorry, the methane one is induced dipole. Yeah, induced dipole. So again, atomic structure influencing electronegativity makes the bond polar, IMFs. So we've got induced dipole, okay, or London forces or van der Waals, depending on your exam board, you use whichever one you're told. Then, of course, we get permanent dipole and dipole ones. So they will obviously be a bit stronger because they're there permanently. And then the one after that, what's a stronger one, intermolecular force than permanent dipole? Permanent dipole. Hydrogen bonding, good. Now, don't forget, this is where we have hydrogen directly bonded to fluorine, to nitrogen, and to oxygen, okay? So any molecules that contain those bonds, you're going to have hydrogen bonding between those molecules or with other things, okay? Now, the reason, why is a hydrogen bond so strong? Well, again, it's down to atomic structure. You've got fluorine atom here, highly electronegative. It's got loads and loads of potential to draw that pair of electrons away from the hydrogen that's bonded to it. Now, if that hydrogen has lost its big difference in electronegativity, absolutely, Alex. But just in your mind's eye, imagine this. If fluorine has got hold of hydrogen's electron that it brought to the covalent bond party, What's left over here? Like literally what is left on the end of this bond over here? Delta plus, it sure is, but it's more than that because it's hydrogen. Good, Alex. It's basically just a proton. So this hydrogen atom was a proton and electron. Well, its electron has been basically stolen from fluorine over here. Like fluorine's taken, it's been stripped down of electrons, and all it's been stood there with in its boxer shorts. And now fluorine's just taken its boxer shorts off it, and now it's just a naked proton. Okay. Yes, absolutely. So because of that, we could say that HF bond is so polar. You could say it's a covalent bond with ionic character. You could say that. Absolutely. Okay. And that's my next point as well, is when you're talking about ionic substances that have covalent character, again, that comes down to atomic structure and your charge density on those different ions and whether there is any covalent character there and stuff like that. Okay. Ansh, please don't do that. Ansh is asking, should I write that hydrogen's just had its boxer shorts stolen in an exam? I doubt it's going to be in the mark scheme. That's all I'm going to say. Just a thought. I don't think it's going to be in the mark scheme, but yeah, maybe stay away there. Okay. So if they ask you questions about hydrogen bonding, how many marks will be given? About why it's so strong. I don't think they will ask you that. I'll be honest. Okay, they're not going to ask you why is hydrogen bonding so much stronger than other intermolecular forces. You're just going to be asked to identify hydrogen bonding and basically just know that one is stronger than the other and so on and so forth. Okay. You need to be able to kind of draw the arrangement of bonding, hydrogen bonding and stuff like that. But my point here is just in your mind's eye, so you have that understanding of why it's so strong. It just helps you remember it. If we understand how things work, we can remember, or why things work, sorry, we can remember those trends and stuff like that. It's really, really important. So that, in terms of bonding, is how atomic structure is really, really important. I'm going to do one more thing here, okay? I think everybody needs to know this, okay? But when you've got your, let's say, CCl, CBr, and CI bonds, okay? So we're talking organic chemistry here. And we're looking to hydrolyze this, okay? So if we reacted it with aqueous sodium hydroxide and reflux, okay? And we ended up as an OH there instead. So our OH minus is coming in here, okay, to our delta plus and hydrolyzing it, or nucleophilic substitution. Why is it easier and a faster rate of reaction for CI than CL? And I think people are already putting the C-double-bond-O is a permanent dipole. CI is the lowest bond enthalpy, so hydrolyzes faster. Absolutely, okay. So lowest bond enthalpy, okay, hydrolyzes easier, stroke faster. Okay, so that's why. Okay, they love this question. They love this question, all exam boards, to be fair. Now, the reason for that comes down to atomic structure. You've got your carbon atom, okay, and you've got your iodine atom, and let's say they're sharing that pair of electrons there, okay, and here's our nucleus, and here's our nucleus. Let's say we've got another carbon atom, so this is carbon and iodine, and this is chlorine, okay? Where would it be? It'd be a bit bigger, wouldn't it? Maybe it's the same size, like that. So carbon and chlorine. Notice how this distance here, because of the size of the atom, greater distance equals weaker bond. Because remember, that overlap of orbitals, that sharing of electrons, it's the attraction between that overlap and the nuclei that are going to dictate, they're going to actually form that bond, okay? So the bonding pair of electrons is further away from the iodine nucleus, whereas here, you can see it's much shorter. So again, atomic radius dictating bond enthalpy. So even even electronic structure and atomic structure influences bond enthalpy in that excuse. In that respect. So yes, Alex, we can mention bond length here, okay? So Edexcel, only this, okay? So bond length versus bond strength, okay? Longer bond,
equals weaker bond. Okay, really important. That inversely proportional. Yeah, you could say that 100%. So that is the bonding part of this. In fact, let's do one last thing. Let's do one last thing in terms of bonding, okay? And that is this. Since we're talking about organic chemistry, so we have an alkene. The bonding alkenes is massively important. We've got two bonds in there. Are they the same or are they different? They are different. They are different. The first bond is a sigma bond. That's because we have an overlap of s orbitals. So it's like this. Okay. And it's very strong. And they are spherical in shape. Look, it's all the alliteration there, okay? So s orbital overlap, sigma bond, they're strong, spherical orbitals, okay? And because that overlap is directly between the two nuclei, that's a very strong bond. And that is the type of bond you get. In any bond, any line you draw in organic chemistry is going to be a sigma bond, bottom line, okay? Apart from the second bond here, which is a pi bond, okay? So this is a p orbital overlap. It is weak, okay? And this is where the kind of alliteration falls down. These are figure of 8 or dumbbell shaped. So we have this overlap above and below. And because it's above and below those nuclei, it gets broken more easily, okay? So we've got this attraction like so. But like I said, it's a weaker bond because there's increased distance. That overlap is not directly between the two nuclei, okay? So less energy needed to break it. It's the pi bond that breaks in any electrophilic addition reactions. It's the pi bond that breaks, okay? And the sigma bond remains. So that's really, really important. So again, atomic structure coming into play in terms of organic mechanisms, okay? Very, very important. Year 13 is my last little section on this before we finish up for the day. Where else do we see this going on in organic chemistry? And that's the reason I'm asking year 13s only. Yasmina, aromatic, everyone else like benzene, 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 benzene. Absolutely, it's benzene. So we have this benzene structure like so. The circle represents the delocalized p electrons, all right? And if we look at the overlap, so if we're looking at these y-axis p orbitals, every single one overlaps with every single one. So what I'm doing here is if I was to break this at one carbon and just put them in a line, okay, this is what you get. You get 6 overlapping p orbitals. And of course, this one then overlaps with that one there. Okay, it does look really messy, okay, when you draw this. The easiest way to draw this for me is from above. So if you've got, remember the 2 balloons analogy, okay, that you're looking at here? If you look down the end of them, so if we're looking at this y-axis p orbital from the top, we just see a circle. So when we've got our benzene ring like so, what we have is this p orbital overlapping with this p orbital, overlapping with this one, overlapping with this one, and so on and so forth. Okay, so that, oh, I didn't quite overlap those, but you see what I'm saying. So that is how we get that delocalized ring system there, like so. Okay, so basically it's like they've formed, it is a pretty flower, yes it is, thank you very much. I just realized that I've done that. With these p orbitals, because they all overlap with each other, the electrons can jump from one to the other, and they do, and they give it stability, okay? So wherever we have a sharing of electrons, okay, a sharing of the electron charge, like when a carboxylic acid loses its hydrogen atom, it's actually stable because what we end up with is this O minus down here isn't just O minus. What happens is that charge is shared and it's made stable, which is why it can act as a weak acid. Okay, so that's going on to something slightly different, but it's the overlap of these orbitals. So there's another link between atomic structure, shapes of orbitals, and bonding. Okay. Right, I'm going to stop sharing my screen. So hopefully what we've learned today is this, that knowing atomic structure, well, atomic structure is the first thing that you're probably taught when your bum hits your seat in September in year 12, okay? There's like 3 rings through benzene. My teacher showed us a different type of overlap where there's 3 rings through benzene. Oh, yes. Okay, yeah, I see what you're saying there, okay? So you have a central overlap on the same plane as the carbon atoms. That's the sigma bonds all the way around between the carbon atoms. And then it's like a sandwich, like an Oreo, yeah? So the biscuits above and below, that's the P overlap at the top and the P overlap at the bottom. Yeah, that's what you're looking at. Yeah, that's it. You say burger, I say Oreo. So yeah, it's just another way of looking at it, okay? It's quite difficult to draw that, and you would not be expected to draw that in an exam, okay? Benzene burgers. Right, so to everybody, summarizing, atomic structure is one of the first things you learn in year 12. At that point, you have no idea how important it is. And then as you go through, you learn all these other things. Yes, ionization energies make sense, okay? They're kind of like synonymous with atomic structure. Of course they are. But redox to bonding, to electronegativity, polarity of bonds, benzene bonding, reactivity of alkenes have all got their roots within atomic structure. So if you understand those fundamentals, even when you get to a question, you think, oh, I just don't know, like, what was that again? As long as you know your atomic structure, you can work it out, okay, from first principles. So having that understanding is really, really important. All right. So hopefully, guys, you found that useful. I know we weren't doing questions today, and I know you're looking from exam practice and exam technique. Don't worry, I've got you covered tomorrow, because tomorrow I'm going to be giving you some hints and tips and some little tricks and stuff to help you attack any calculation questions. Okay, I'm going to be giving you all my best advice just to kind of ease those nerves and just give you a bit of confidence moving forward. Okay, so I'm really, really pleased you found this useful. So thank you guys in the Zoom. YouTube, anybody watching in YouTube that wants to ask me any questions at all about the lives coming up or what I've just been talking about, that is up to you. I'm really glad that the guys in the TT members in the group found that really, really useful. So pleased with that. So YouTubers, where are we? How would you find that? Okay, if you like this, then just give us a thumbs up. That'd be awesome. And you know what? Let fair's fair. If you didn't like it, just give us a thumbs down. Hopefully you found it really, really useful. Like I said, it's not exam technique. It's more about just having this broad understanding. I want to give you confidence. All right. So I will be doing calculations tomorrow. There will be a PDF. So when you click on the link tomorrow in YouTube, or indeed in the live class pages within the course, then you can click on the PDF and you can work along with me. Okay, I'm going to be giving you some timed questions to have a go at tomorrow, but I'm going to give you some techniques and some tricks to help you kind of minimize those errors that can creep in calculations. So it still happens to me, it happens to everybody. Okay, so I'm going to be giving you some really quite tough questions tomorrow. I'm going to start easy. I'm going to be working our way through up to like more difficult, like redox titrations and stuff like that. But the principles, I hope you'll see, are exactly the same. From the simplest calculation to the most difficult one. There's always the same place to start. There's always the same format. Okay. So I will love and leave you now, guys. Thank you very much. And I will see you tomorrow at 11 o'clock. Don't forget, if you want to get involved in the chat and the Zoom during the live class, join the live free trial, the free trial, a 7-day free trial. There's a link in the description underneath. You can do that anytime you like. No commitment necessary. Won't cost you a penny. But I'd like to think that you find it very, very useful and you want to stay with us and be with us while we help you through these very difficult assessments over the next few weeks. Okay, so wishing everybody the best of luck. And yeah, look after yourselves, and I will see you tomorrow. Ronnie's on at 1 o'clock today with maths,
and Rich is on at 5:30 with some biology for you. Okay, so share the love. Okay, if you think anybody would find these sessions useful, then just let them know, send them a link, just give them a nudge, and like I said, give us a like. And thank you very much, guys. I will see you very, very soon.